Hi everyone, we are back and we're going to look at some vibrations examples. Specifically, we're going to look at the case of a block on a conveyor belt anchored to a wall on a spring. So here we can look at essentially some of our Newton's equation. So we're looking at a system, we're going to have some friction, we're going to have our spring equation, we have some velocity of our belt. We can develop, as you have hopefully done in your vibrations course, basically Newton's equation for the block. So we can see essentially again that x displacement, that acceleration, F equals ma, equals essentially our spring function. So how is that going to vary as a function of x? Our friction, which is again velocity of the belt, and then we could set up some boundary conditions. So this is a second order ODE, when we know x position here, it's going to be some value here, x prime here is going to be 0, and then we can go ahead and start to solve for our system. Specifically, we can look at the position, we can look at the velocity, and then we can see essentially our solution. And actually, we could vary lots of different variables here. So you can see as you change the friction coefficient, how does that change the position? How does that change essentially the velocity of my block on the conveyor belt? As we change the velocity here, again, you see that magnitude changing, but the spring constant really kind of tells you if I have a strong spring, actually a large spring constant, you see that, I'm reducing essentially that variation. Essentially you're saying here, mass the block, you can kind of see how that changes that as well. It takes a longer time, those undulations. You could also look at the case of basically a spring mass system where it's pushed down and then released. You could see the simulation of that going on right here. So pushed down with some force, then released. Again, we're going to have some function where we're pushing down. We have some initial condition for that velocity. So this is our basically equation of motion. One initial condition will satisfy this, solve it, and you can see that position. And you can see, again, time t equals 0. Oops, let's go ahead. Do it large undulations, and then it starts to decay. So if it's over damped, we can kind of see those different values here. What about a string with fixed length? So you can look at your equation of motion again. So again, I'm looking at undulations of that spring, second order. You can see here, second order with time, second order in x. So I'm going to have my two boundary conditions. Here I have my two initial conditions, and then I'm going to solve. When I look at those solutions, I can look at them as a function here, looking at it varying time, x, m, and all those values. So again, it's a solution. It can give you an infinite number of harmonics. If you're looking at the general solution, and then you can kind of see, extract first four components here. Oops. I think we may be missing one here. But we can look at actually the active here. So actually we can set these up here, set this up here. We'll look at our D-solve here. We can plot this. I'm missing. So if we look at our solution, oops. So let's look back at our equation here. Our boundary conditions, initial conditions, we can solve that here. We can solve that here, we got that. We can change that initial condition, keep that boundary condition. We should be able to get that. And then, let's see here. So we're getting essentially a value here. So we want to look at the first four values here. It's giving us this value. It's clear. So here we have a little bit. Let's look at D-solve 1. So let's look at T. What does that look like? And let's slash that. Infinity goes to say 10, and it doesn't like to, it gives us the values we want to look at it for. So we have these values of m here, 0 to 4. Let's look at activating it. So here we've got our solution. Here we go. You set that equal. Solution x, comma, t, comma, set equal here to u of x and t. Oops, let's figure out what's happening here. But actually, we could take this. We could actually do something a little bit more elegant. So we could set this as my function string. And I could do basically plot string. Actually, look at this. Except slash dot x goes to x1. And we want to plot this. And then we want to go from, again, t goes to t1, and we want to go t1 here. And then we can look at some of these values. Look at my fun string should be able to plot that. Actually, let's do that. Let's do it. Look at the different times. It's not liking that function for some reason. Fun string. Let's look at here. Because for some reason my fun string is not giving me my values of t for some very odd reason. There we go. I don't know why that was not liking it, but now we can see those undulations of my string. Anyways, that's fun. You could also model a ball bouncing down essentially steps. So again, there's lots of different equations of motion that you could kind of look at. My favorite example is essentially the DVD screen. And looking at these, you could look at resonance. So you could look at an undamped response. You could an underdamped near resonant type response. You could look at a damped response. So you could do lots of phenomena looking at essentially harmonic oscillator type solutions. So you can look at damped, over-damped response, damped near resonance, heavily damped, and all of these good things. You could also look at RLC circuits, and we'll get into that. RLC circuits and Schrodinger's equation next time when we get into this, as well as some solid mechanics examples as well, and some beam bending. So next time we're going to get into RLC circuits and our Schrodinger's equation. So see you then. Thanks.